the opportunity. Well, I will try to first to give you some example, the context of this, of the piecewise hereditary algebras. In this talk, I consider K an algebraically closed field, and A is a finite dimensional algebra, K algebra. And mod A is the category of finite generated A modulus, right A modulus. Okay. And H to me here is a hereditary category. This means that the x2 is 0. Well, in this first picture here, represents to me the hereditary algebras. An algebra is hereditary if the submodels of projective modulus is projective. In general, if H is an hereditary algebra, we can represent this algebra is a pet algebra, and the Q is a quiver without cycles. We can represent in this way, okay? This class of algebra, we can, we know that we have the representation finite algebra, the tame algebras, and the wild algebras. The representation finite means that the modulo category, the number of isoclass of indecomposable modulus is finite. Here, the tame algebra, you can think that we can parameterize the modulus here, and the other is wild. For example, the representation finite algebras, the representation finite, we know that this kind of algebra, the quiver is dinking. And the dinking, we have the type AM, the type DM, and the other is E6. E7. And E8. And the tame algebras, we have the quiver of the tame algebras. Here is the graph, okay? We represent in this way, and we have another vertex there, and here we have the type DM2. The other is 6A2, we have a this kind, E7 tilde and E8 tilde. And the others is wild. Well, we have another class of algebras that we call canonical algebras. And I will put these here in this picture here, and we have three kinds of canonical algebras. I will explain what is the relation between canonical and hereditary. Here is the, well, here is here is the tubular algebras and wild algebras, wild canonical algebra. Well, the definition of canonical algebras. Yes, wild, tubular, and tame. I will explain the relation between, I will define first canonical, and after I will explain the relation between the canonical and this. In the canonical algebra, we fix some integers, and some parameters here in the field, and the quiver of canonical algebras is something like this. The vertex I will represent in this way. We have some reason to do this, I will explain after. And here the vertex is P0 minus 1 x0, and here is C, x1, P1 minus 1, here is C, and xn, and here is Pn minus 1, and C. Well, the canonical algebra, we take this quiver, the pet algebra that is generated by this quiver, with and bounded by the following relation: xi pi minus x0 p0 plus lambda I x1 p1, and I from 2 to n. Well, in the case that n is equal to 1, then we don't have this the relation, and this is a canonical algebra of type P0, P1. In this case, we don't have relation, then this canonical algebra is hereditary, is something like this, okay? In the case that n is 2, then we have the relation, because here we have lambda 2, and we have this kind of canonical algebras. If we choose the parameters here, 2, P2, and 2, 3, 3, 2, 3, 4, and 2, 3, 5, it's possible to prove the following. I will call this kind of algebra C, P0, P1, P2, okay? This kind of canonical algebra in the case that n is 2. It's possible to prove that to this algebra we have a kind of module that we call tilting module. I will define after, okay? Here in this algebra. For example, in the case that is 2, 2, P2, it's possible to prove that with this modulo, it's possible to find a modulo in this category such that the endomorphism ring of this modulo is isomorphic to an algebra of this kind here, to this kind. And then the derived category of this algebra is derived equivalent to C2, 2, P2. Well, the same thing to the others here. It's possible to find a tilting module such that we have this kind of properties, and this is derived equivalent to this kind. This other here is derived equivalent to E6 still, and E7 and E8. So to n equal to 2, is this the relation between canonical algebra and this algebra, okay? Now, there is another relation between to the other canonical algebra, but I need to explain something more, some other things. First I will define what is a tilting. In the case that we are in a hereditary category, we can define a tilting object there here if the fact t is equal to et, and this means the modulus, the quotients of modulus are factors of finite direct sums of t. And these are the modulus such that the objects such that xt is 0. Then an object is tilting in a hereditary category if this set is equal to this set. Or this to hereditary, but if we have a finite dimensional algebra, we can define a tilting here in the following way. The projective dimension of T is at most 1. We don't have extensions. 1 here. And the third condition is that the number of summands of T is equal to the rank of the Grothendieck group of A. This is a tilting. Well, there is a common frame to this kind of algebras that is the following. For example, if A is an arctic algebra, and well, a finite dimensional algebra, A finite dimensional algebra, such that the derived category of mod A is equivalent to the derived category of a hereditary category. In general, we call this A is called piecewise hereditary algebra. Well, in this case, for example, if A in general, in this case, we know that A is and T, where T is a tilting complex. If you have this kind of equivalence, is a equivalence between this triangle equivalence between these two categories, then it's possible to find a complex such that we have this. Well, a tilting complex is a complex that satisfies the following. And add T is the category of summas of T. This generate the category the derived category. Yes, generated in the sense of triangles. We take the objects and with the triangles you can construct the category. Well, then I'd like to use this to explain the relation there, because, for example, in the case that here T is a tilting complex in general, but if T is here in the category H, then it's possible to prove that this algebra A we have is a canonical algebra in general. This algebra is something that then we have here canonical algebra. But in the case that T is here, well, and there is another contest, another relation that I like to explain too. But first, it's important to say this: the following result. Let H be a hereditary category with tilting object. If H has some non-zero projective object, then H is mod H, where H is a hereditary algebra. Then, if the category, the hereditary category, has projective object, then the category is of this finder. This means that is this kind of algebra that I talked there. Well, and if you don't have projective objects, then we have the following. I have more 10 minutes, yes? Okay. Well. Oh, yes, yes, yes. Then, fix some integers, a parameter family, and we take LP is the rank 1 abelian group with the generators x0, xn with the following relation: p0 and pn xn, and with this group we have the LP graded algebra. Here S to me is this algebra. We can graduate this in this way. And to each parameter of this, we can attach a two-dimensional variety. I call FP lambda. Is a variety of an plus 1 that is given by the following equation: xi pi is equal to x1 p1 minus lambda I x0 p0. Then we have this the homogeneous polynomial. Then we can consider this quotient. SP is this, considering this graduation here. Then we have this quotient. Then this is LP graded algebra 2 with the graduation induced by this. And was a set, we have a weighted projective line. That we call in this way. This consists of the LP graded prime ideals SP of SP lambda. Well, then we can equip this with the Zarix topology and with a sheave, a structural sheave. And it's possible to prove the following to this. If H is a hereditary category with a tilting, we have that with a projective object, we have this. And without projective object, we have that this is derived equivalent to this. Sorry? Oh, sorry. Here. The other possibility is that this is derived equivalent, or then here I don't put projective object. Then we have the following. Then if H is hereditary category, then we can say that H is mod H, or The derived category of H is the category of coherent sheaves on a weighted projective line. Well, now what is the relation between, in general, between piecewise hereditary algebra and this kind of category of sheaves? We proved the following result. Then I need to explain what is a mutation. Take T is a tilting complex here in the derived category of hereditary category, and we choose a decomposition of T such that we don't have morphism from T2 to T1. And then we take another T approximation, as a T1 approximation of T2. This is a morphism such that if you have another morphism of this category here to T2, then this morphism factorized to this morphism. Then this is an approximation. With this approximation, we construct a triangle. Here is T1 prime, and here we have this. And it's possible to prove that T prime T1 plus T2 prime is a tilting complex. So, in general, if we have this kind of equivalence, then it's possible to find a sequence of tilting mutation from an algebra of this kind of an algebra NDT, where T is a tilting here in H. It's possible to find a sequence of mutation until to arrive in this algebra. Well, this is a result with Lemur and Marcus. Well, then is the following. If we have the derived equivalence, then in general, and I am supposing that that H is not hereditary. Okay, then there exists L and a sequence T0, TL, a sequence of tilting. Okay, this is tilting complex, such that the first guy in this sequence is in H, and TL is A, and TI is obtained from Ti minus 1 by tilting mutation. Well, then this is a result of. Then, in general, this kind of piecewise hereditary algebra, we have this kind of relation between this algebra with the canonical algebra or the hereditary algebra. Then we can do this kind of mutation to arrive in this algebra. Well, there is some more things about this, but I finish. I don't understand the question.
So there are diagrams
In physics?
that appear in physics 10, 11.
Uh-huh.
So maybe the answer.
Ah, here? No.
The category of models is Y. So the models itself you cannot compute them. To classify the model is equivalent to the word.
Yeah, but maybe here that's the point. Whether they're canonical.
This, in the case of Wilder, is so difficult. In general, you can think when an algebra is Wilder, if you take any other algebra, it's possible to define a functor from the category of this algebra to the Wilder algebra. You can choose any algebra and you can do this. A functor, a faithful functor, then from the modular category to the Wilder. It's so wild.
Hereditary.
Sorry?
Hereditary.
No, it's not hereditary. And this yes, but this kind of algebra, we have, how can I say? It's called tubular because when we do a picture of the category, we have something like this. It's possible to construct the Auslander-Heighten quiver of this algebra, and we have a family of families of tubes, and something stable here. Stable means that we have the Auslander-Heighten translation. You can apply here to the right and here to the left, and here is the representation of the quiver is tubes. It's family of family tubes.
It's starting. It takes time.
It takes time.